we're going to examine periodic trends that we can see on the periodic table with atoms, molecules, and compounds and how they relate to some of the intermolecular attractive forces. First, we're going to take a look at trends that we can see in molecules, also known as covalent compounds. And then second, we'll take a look at periodic trends that we can see in ionic compounds related to their melt points. Let's first take a look at the family known as the halogens with fluorine, chlorine, bromine, and iodine. All of the halogens would be referred to as being nonpolar diatomic molecules. Being that these are all nonpolar, the only attractive forces that exist between molecules are dispersion forces. As we look at a periodic trend, as the mass of each halogen increases, which indicates that the size of the diatomic molecule is increasing, we can see a corresponding increase in the boiling point for each one of these compounds. As we move down the family on the periodic table, the size of our atoms is increasing, so the size of the diatomic molecules is also increasing. With an increase in the size of the electron cloud as we go from fluorine to chlorine to bromine to iodine, with an increase in the size of the electron cloud, the size of the temporary charges that get generated also increases. With an increased size of temporary charge, the size of the dispersion forces generated between particles increases. An increased charge from a larger electron cloud generates a stronger attractive force, and we see that reflected by an increase in the energy required to make the particles go from liquid to gas or separate and break the dispersion forces that exist between molecules. We see a similar periodic trend looking at a group of hydrocarbons. These are all straight chain hydrocarbons, and we notice that as the mass or size of the molecule increases, we see a corresponding increase again in the boiling point of this particular material. Now, all hydrocarbons are considered nonpolar molecules, so once again, the only attractive force existing between molecules is dispersion forces. In a small hydrocarbon, such as methane, CH4, the electron cloud is fairly small, so the amount of dispersion forces that can be generated between molecules is fairly small, which is reflected by a fairly low boiling point or energy that's required to separate these particles and turn them into gaseous particles. Whereas if we look at a longer chain hydrocarbon such as C5H12, there's multiple locations for dispersion forces to create an attractive force between a much longer and larger electron cloud. The total force of these increased dispersion forces we see with a much higher boiling point for something such as pentane. It's almost 200 degrees higher than what we see for our methane molecule. It's merely because of the increased size of the electron cloud generating stronger and larger dispersion forces. The next pattern, we have two molecules, water and methane, where we can see that their masses are relatively the same. We would expect the electron clouds then between water and methane to be fairly similar in size. And yet we can see, even though they're similarly sized molecules, there's a marked difference in their boiling point, where water is 250 degrees Kelvin higher than the boiling point of methane, even though the particles or molecules here are very similar in size to one another. The reason for such a marked difference in the boiling point of two similarly sized compounds is that very polar water molecule has the capacity to make hydrogen bonds between molecules. The hydrogen bonds are very strong and give water a fairly high boiling point, even though water has a very low molecular mass and a fairly small electron cloud. The nonpolar methane molecules could only form the fairly weak dispersion forces between neighboring molecules. The weak dispersion forces would account for the fairly low boiling point relative to water, which indicates a lesser amount of energy required to separate methane molecules from one another. We have another pattern to look at here. We have the molecule HF, hydrofluoric acid, which has a fairly high boiling point. Then we see a trend between hydrochloric to hydrobromic to hydroiodic, where the boiling point increases gradually from one to the other. But of all of them, the hydrofluoric has the highest boiling point. Now again we see that HF has the capacity to form the very strong hydrogen bonds. So even though that hydrogen fluoride, hydrofluoric acid, is the smallest in this group, it has the highest boiling point because it can make the very strong hydrogen bonds between neighboring molecules. Now all of these, HCl, HBr, and HI, are polar molecules, so they're going to create dipole-dipole attractive forces, where the negative portion of the molecule will be attracted to the positive portion of a neighboring molecule. However, we also see that HI has a much larger electron cloud than what we see in HCl. So both molecules also generate dispersion forces, but it's the larger electron cloud in the larger HI molecule creates a greater dispersion force. So what we see is we go from HCl to HBr to HI, even though the molecules are all polar, the HI with the larger electron cloud and greater dispersion forces shows the highest boiling point. However, the HF with the hydrogen bonds, even though it's the smallest molecule of the series, has the highest boiling point, since the hydrogen bonds have a greater attractive force than the dipole-dipole dispersion combination shown in the HCl, HBr, and HI. The compounds we've looked at thus far in the trends are for molecules and covalent compounds. With covalent compounds or molecules where dispersion forces, dipole-dipole, and hydrogen bonds are of consequence. The next series of trends we're going to take a look at are specifically for ionic compounds. In ionic compounds, dispersion forces, dipole-dipole, and hydrogen bonds are of little to no consequence. In ionic compounds, the primary attractive force that determines many of their physical properties is that we have a strong electrostatic attraction between oppositely charged ions, which creates what we call ionic bonds. The first compounds we'll take a look at, we have lithium fluoride and magnesium oxide. And let's first note that the melting point here, 845 degrees Celsius, and for magnesium oxide, 2800 degrees Celsius, merely to melt this or turn it from a solid to a liquid. That's a tremendous amount of energy. Now, one thing to consider in ionic compounds, there's no sharing of electrons. In lithium fluoride, the fluoride has actually swiped an electron from the lithium and become a -1 ion. The lithium, having lost an electron, is now a positively charged 1+ ion. What now exists between the ions is a very strong electrostatic attraction between the +1 and -1 ions. But one thing we can see here is the lithium fluoride and the magnesium oxide have markedly different melting points. Magnesium oxide at 2800 degrees is a much higher temperature than the lithium fluoride, indicating the attractive forces for the magnesium oxide must be much greater than what we see in lithium fluoride. Now, all of the ions here, the lithium, the fluoride, the magnesium, and the oxide, are fairly similar in size. Since these are similar in size, the distance between the centers of our ions is going to be roughly the same, or fairly close to one another. Now, if we recall Coulomb's law, which gives us the force of attraction between electrostatically charged particles, if the distance in both these is roughly the same, the force we would generate would be roughly the same. What's different in our ions is the lithium is a +1 and the fluoride a -1, whereas the magnesium is a +2 and the oxide is a -2. The change in the size of our charge changes our values for Q1 and Q2 in Coulomb's law. The magnesium oxide with a +2 -2, with values of +2 -2 for the magnesium oxide, the size of the force that we would generate would be 4 times as big as the force we would see for our lithium fluoride with the +1 -1 combination of ions. It's this increase in electrostatic attraction from a +2 -2 combination that gives us this marked change in melting point from 845 up to 2800 degrees for magnesium oxide. We see a similar pattern when we compare sodium chloride, which is a +1 -1 ion combination. that we see the sodium chloride has a melting point of 801 degrees, where it's a +1 -1 ion combination, compared to calcium sulfide, which is similar size ions, where we have the +2 -2 combination for calcium sulfide, and the melting point changes from 801 all the way up to 2673 degrees Celsius. We see another pattern emerging. Lithium fluoride, which is +1 -1, sodium chloride +1 -1, and potassium bromide, there's a change in melting points with these different ions. Now, because as we go lithium fluoride, the sodium chloride, the potassium bromide, we're moving down the periodic table. Even though they're all +1 -1 ions, the size of the ions increases as we progress down the periodic table. What happens with the change of the size of our ions, even though these are all +1 -1 ions, so the size of our Q1 and Q2 is remaining the same, the ionic radius is changing, which changes the size of our distance for Coulomb's law. Now, one thing about Coulomb's law is the distance in here is measured from the center of charged object number 1 to the center of charged object number 2. So what we see is we move from lithium fluoride to sodium chloride to potassium bromide. With an increase in ionic radius, the size of the distance measured from center to center in these ions increases as we go from lithium fluoride to sodium chloride to potassium bromide. If our distance here increases, because it's in our denominator, that means the size of our attractive force is going to decrease. We see a decrease in the strength of the attractive force reflected by a lesser quantity of energy necessary to melt these compounds as we go from 845 to 801 to 734 degrees to melt each of these ionic compounds. An item of note that's indicative of the strength of the attractive forces in ionic compounds is that at room temperature, all ionic compounds are hard crystalline solids, which is an indication that the attractive forces in ionic compounds are extraordinarily strong, which is the case for ionic bonds that exist in ionic compounds.